Column buckling is probably the best known buckling phenomenon, in which a compressive load is applied to one end of the column. For small loads, the column remains straight, but for some special compressive load, the column bends dramatically. That dramatic deformation is called buckling, and the special value is the buckling load. As the buckling load is exceeded, the column continues to bend more and more and will eventually break. A slender beam can also buckle because it's spinning around its axis. In this case, the centrifugal force causes the beam to buckle at some critical angular speed. What's really interesting, however, is that increasing the speed or adding more energy to the system can cause the beam to unbuckle. Let's see this in action with a wooden dowel and a standard variable speed drill. The dowel is inserted into the drill chuck, and the left end is supported by poking the dowel through a cardboard box. You can't buy a straight dowel, and it's very slender, so it does sag under gravity. However, as the drill speeds up, which you can tell by how loud it is, the beam buckles or whirls considerably, and it spins around in a bent configuration. Then, as the drill spins even faster, the dowel straightens back out. Let's briefly step through the math for the simplest possible model for this phenomenon. Consider a beam with a constant cross-section and assume that the material is isotropic, so it behaves the same in every direction, homogeneous, so it's the same from point to point, and elastic, so it stores all the work done on it. The wooden dowel, of course, has a circular cross-section, but let's start with a more general case. The equations of motion are a system of two partial differential equations, or a single vector PDE. W is the displacement of the beam in the xy plane. So for a straight beam, the vector W is 0, the trivial solution. Omega is the angular speed of the beam. E is Young's modulus, which indicates how stiff the material is. Rho is the material density. A is the cross-sectional area. I1 and I2 are the principal moments of inertia for the cross-section. And dots indicate time derivatives, and primes indicate differentiation with respect to z. We're looking for non-trivial solutions of this system. The governing equations consist of four terms. The first is the inertial term, the A in F equals ma. The second term is the Coriolis acceleration, which tends to straighten the beam, whereas the third term, the centrifugal term, tends to cause the beam to bend. Finally, the fourth term is the bending term itself. The math is simplest if we assume that both ends of the beam are simply supported. That's not the case for the end inserted into the drill chuck, but we will address that later in the video. A simply supported end means that the beam cannot move in the x or y directions, but it is free to bend at the end. And we take the length of the beam to be L. So let's look for solutions of the form e to the lambda t times the sine of n pi z over L times a constant vector w. A solution of this form automatically satisfies the boundary conditions. At the moment, lambda is an unknown constant that determines the time behavior, and w is an unknown constant vector. If w is identically 0, then the beam remains straight. So to observe whirling, we seek a non-zero w vector. Solutions of the governing equation are stable if the real part of lambda is negative. Plugging the assumed form for the solution into the governing equations gives the matrix equation at the top of the slide. We find whirling if the determinant vanishes, which gives a fourth-degree polynomial equation for the unknown constant lambda. Now, in the interest of time, I won't show every step in the calculations, but hopefully there's enough detail here for anyone who is interested to fill in the missing steps. Without loss of generality, let's assume that I1 is less than or equal to I2. Remember, I1 and I2 are principal moments of inertia in the cross-section. So whirling occurs in intervals shown. As you can see from the graph, as omega is increased slowly from 0, the beam remains straight until omega hits the first red region. There the beam whirls or buckles in that region. However, like we saw in the video for the dowel rod, increasing omega even more eventually moves us out of the first whirling region and the beam straightens out. However, if we keep increasing the speed even more, that causes us to encounter a second whirling region. We're not able to observe this behavior with the dowel. I would need a more powerful drill or a longer dowel. In the second whirling region, the beam looks different than it does in the n equals 1 region, which may remind you of standing waves on a string. Again, you can continue to increase omega to straighten the beam out again until you encounter the third whirling region, and so on. I'm told that it's not uncommon for machines to operate at speeds above the third or fourth buckling regions. Now, earlier I claimed that the Coriolis force is responsible for straightening the beam back out. Let's observe that in the mathematical model. The Coriolis effect is manifested in our equation for lambda in the red term. If we simply remove that term, then the resulting model predicts that the beam whirls for all omega over the smallest buckling speed. Therefore, it is the Coriolis force that causes the beam to unbuckle. For the dowel rod, and for a lot of applications, the cross-section is circular, so I1 and I2 are the same. And with a solid circular cross-section, I1 and I2 are both pi r to the fourth over 4, and the cross-sectional area is pi r squared. With equal moments of inertia, the buckling intervals collapse to single points, indicated by the dots on the axis for omega in the graph. Finally, we revisit the boundary conditions for the drill end of the dowel, where the beam cannot move in the x and y directions, but it's also not free to rotate. So W is 0 at z equals 0, and the partial derivative of W with respect to z is also 0 at z equals 0. Before, we assumed that the second derivative with respect to z was 0, so this is a little bit different. The resulting form for W involves both circular and hyperbolic trig functions, but we obtain similar intervals for omega at which whirling occurs. We're going to hide a lot of the details here. The only real difference in the answer is that n pi over L has been replaced by mu sub n, which are the values of mu such that the tangent of mu L equals the hyperbolic tangent of mu L. Since mu sub n is larger than n pi, the whirling frequencies are higher here than they were before. So putting the one end of the dowel into the drill chuck effectively stiffens the beam. Let's watch the physics in action one more time.